This lesson introduces diagnostics to identify unusual observations in a regression model. In multiple regression, a case can be extraordinary by having an unusual y value compared to the model, an outstanding x value for one of the predictors, or an unusual combination of x values. In simple linear regression, a high leverage point is easy to spot because it is far from the mean of the x values in a scatter plot. In multiple regression with multiple predictors, a point might not be far from any of the individual x means, yet still exert large leverage because it has an unusual combination of predictor values. Because of this, it is easier to detect a high leverage point in multiple regression using a statistic to quantify the amount of leverage an observation has. The statistic for leverage is relatively simple for a simple regression, but gets more complicated when we have multiple predictors. Fortunately, R will calculate leverage for us. Here's the rule of thumb for defining the amount of leverage an observation has. For k predictors, a leverage value greater than twice the sum of k and 1 divided by sample size n is considered moderately unusual in terms of leverage. If h, the leverage value, is greater than 3 times the sum of k and 1 divided by a sample size n, then the observation is considered to have very unusual leverage. Let's return to our roller coaster example. What if we wanted to predict the speed of a roller coaster based on its height and drop? Our regression model of speed on height and drop plus the interaction term of height and drop gives significant p-values for the overall f-test and for the height and drop terms. The interaction term is significant at the 5% level. This model explains 86.3% of the variation in speed of roller coasters. We have two predictors, height and drop, in our model, so k equals 2. We have data for 76 roller coasters, so n equals 76. Plugging in these values gives us our bounds for moderate and high leverage. If any coaster has a leverage greater than 0.089, we say it has moderate leverage. If its leverage is greater than 0.1184, we say it has high leverage. Using these two lines of R code, we can compute the leverage for each coaster and plot them to identify any extremely high leverage points. We see the top 11 leverages listed in the sorted table. 10 coasters have a leverage above 0.0789 and 4 are above 0.1184, but 3 are very extreme when looking at the distribution. 2 of those coasters, the Millennium Force in Ohio and the Steel Dragon 2000 in Japan, have unusually high peaks and drops of over 300 feet. The third high leverage point belongs to the Oblivion in England, with a height of 65 feet and a drop of 180 feet. Wait, how is that possible? How can the drop be greater than the height of the coaster? Did you guess it? The Oblivion drops into a hole in the ground. With a height of only 65 feet and a drop of 180 feet, this coaster definitely has an unusual combination of height and drop. Would you like to ride this coaster? Oblivion's leverage should make us think about conducting further regression analysis, one without Oblivion. The more complex the regression model, the more important it is to look for high leverage cases and their effects. Recall that a residual quantifies the deviation of an observed value from the regression model used for prediction. A standardized residual divides the ordinary residual by an estimate of its standard deviation. Essentially, the standardized residual is quantifying how large the residual is in standard deviation units. Just as with z-scores, this makes it easier to identify outliers, in this case, unusually large residuals. A studentized residual is a standardized residual with the exception that the standard error is replaced with the standard error of the model fit without the observed value. Standardized and studentized residuals follow t-distributions, so values beyond plus or minus 2 and plus or minus 3 are considered moderately and highly extreme. Let's calculate the studentized residuals for our regression model of speed on height and drop. Using the 2 lines of R code shown here, we can view a sorted list of studentized residuals for our model. Note that there are 3 coasters that have unusually large residuals: Accelerator, Hypersonic XLC, and Volcano the Blast Coaster. A case with both high leverage and large studentized residual is likely to change the regression model substantially all by itself. Such a case is said to be influential and cries out for special attention, because removing it is likely to give a different regression model. We use a statistic called Cook's distance to evaluate influence. If the value for Cook's distance is greater than 1/2, suspect possible influence. If Cook's distance is greater than 1, strongly suspect possible influence. If the value for Cook's distance is extreme in the distribution of all Cook's distances for your data, the observation is almost certainly influential. Let's look at the Cook's distances for our coasters. Using the lines of R code here, we can calculate the Cook's distance for each coaster and display in a sorted table as well as a histogram. Note that none of the Cook's distance values are greater than 1/2, but there are a few that are extreme in the distribution of Cook's distance values. These should be investigated. We already understand Steel Dragon's outstanding status, as it has an unusually high height and large drop. Further investigation reveals that the other 3 are mechanically accelerated, not simply gravity-driven. These were the 3 coasters with very high studentized residuals. What happens if we exclude these 3 from the data and rerun our regression model without them? Rerunning our regression model without the 3 accelerator coasters has a striking effect. Do you see it? Pause this video as you look at the output to find the surprising effect of removing the 3 mechanically driven coasters. What is the surprising effect of moving the 3 accelerator coasters? Let's look at the p-values for this model. While the p-value for the overall f-test is significant, we see the p-values for the height term and the interaction term between height and drop are both large, indicating they are not statistically significant. In other words, height is no longer important to the model. So we can drop those terms and rerun a simple linear regression of speed on drop alone. Our simple linear regression of speed on drop without the mechanically accelerated coasters gives a significant p-value and an R-square value of 92.3%. In other words, 92.3% of the variation in speed of a roller coaster is explained by the amount of drop in this model. Again, this is excluding the 3 mechanically accelerated coasters. An alternative to omitting an unusual observation is to keep it in the data set but construct an indicator variable that is 0 for all cases except the one we wish to isolate. This is equivalent to omitting the case, but it has 2 advantages. It makes clear to others which observation is extraordinary, and the p-value for the indicator variable's coefficient tells us whether the case is influential. Let's try this with our mechanically accelerated roller coasters. First, we create an indicator variable for each of the 3 coasters. Notice that the value of accelerator is 0 for all coasters except the accelerator, for which it is 1. Similarly, we create indicator variables for Volcano the Blast Coaster and a Hypersonic XLC. We add these variables as columns to our original data set. The significant p-values for all three indicator variables confirm that the BLAST coasters don't fit with the other coasters. When both high leverage and large studentized residual cases are present, it is irresponsible to report only the regression on all the data. Investigate the unusual cases and discuss them individually if they offer insight, but compute and discuss regressions with those cases removed.